Assalamu alaikum and welcome to lecture number 6. In this lecture, we are going to discuss some of the numerical problems which were some of the numerical problem based on the discrete time signals, periodic signals, and mainly this lecture is about the unit step function, unit impulse, rectangular pulse function, signum function, ramp function, and sinc function. So let's start with where we left in the previous lecture. So we are on this slide in the previous lecture, and we are going to discuss the whether the given signal is periodic, right? So these are the this is the discrete time cosine signal, right? So the expression for this is x of n equals to cos of 2 pi n by 12, and its continuous counterpart is this one. So because you understand the difference between the continuous and discrete time periodic signal, right? So that is the for a signal to be periodic, the condition in case of continuous time is that it should have the period should be positive, and that's all. But in case of the discrete time case, the period should not only be positive, but it should also be integer, right? Now to find the period, so uh, due to the constraint of the integer, right? So that the period of the discrete time signal must also be integer. It's not necessary that all the sinusoidal signal in discrete time case are periodic, whereas in case of continuous time signal, all the sinusoidal signal, they are periodic, right? So if we talk about this signal, the period for this signal is very easy, that is 12, right? So you understand in case of uh, continuous time signal, the relationship between period and the frequency is that is the it should be equal to 2 pi, right? This 2 pi, so that's very simple. You can find the relation for the period, which is equal to 2 pi by omega naught, right? So by putting value, because omega naught here, it is going to be 2 pi by 12, so putting 2 pi by 12 here will result into 12 seconds, right? So this is how you find the period for a continuous time case. But as far as the discrete time is concerned, right, the period n equals to m into 2 pi by omega naught. So alright, so omega naught is basically the frequency of the discrete time signal. So in this case, the frequency is going to be 2 pi by 12, so simplification results into 12 into m. We know m is an integer, positive integer, so that means this is equal to putting m equals to 1, period will be 12, putting m equals to 2, it's 24, 48, and in fact 24, and then 3 are 36, right? 36 and so on, right? So the smallest value of this period is 12, so that means the fundamental period of this discrete time sequence is 12, right? So similarly for this case, I hope you can easily find that if you find this one, so you know n equals to 2 pi by frequency, so frequency here is 8 pi, right, by 31. So that means you get 2 pi, so it results into 4, so into m, right? So that means you get 31 is divided, double divided, so it will come here. So that means we have 31 by 4 into m, right? So putting m equals to 4 or integer multiple of 4 or integer multiple of 4, multiple of 4 will result into rational number, right? So this will result in a rational number. So that means it is a periodic with period m equals to 4, so it will be 31. When m equals to 8, it will be 62 and so on, right? So this is how you find the period. And whereas for the case of the continuous time signal, this is frequency, so dividing this by dividing 2 pi by this frequency will result into a period which is 31 by 4, right? So you understand this is a positive value, so that's a periodic, whether it's rational or irrational or whatever. But in case of the discrete time, the necessary condition is the period must also be integer, right? So again, for this case, if you look at this one now, this signal is periodic, this continuous time signal is periodic with period 12 pi. But in case of discrete time signal, by putting values here, we get a 12 pi m. So there's no value of m for which we get the product of all these results into rational number, right? So that's why, although cos of t by 6, which is a continuous time cosine waveform, it's a periodic. But in case of discrete time cosine waveform, which is n by 6, this is not a not a periodic signal, right? And you understand why, because the condition for periodicity in case of discrete time signal is that it not only the period should be positive, but it must also be integer. So that's why cos of n by 6. So that means not all the discrete time sinusoidal signals, they are periodic, whereas in case of continuous time, we say all the continuous time sinusoidal signals, they are periodic. Okay, so this is a homework. Maybe you go through it and you understand how to find the period. You can say again, because we have two signals, right? So the frequency of this signal is this one, so you can find the period, and again this one, and you can find the period, and you understand how to find the period. So it should be something like n1 is the period of one signal, n2 is the period of second signal. So either you can go and find the LCM, okay, or you can write like this, and you write like this, and then this should result into rational. But you understand, for the case of discrete time signal, just you need to write them in co-prime form, because that's understood. In case of discrete time signal, they are always it will result into always rational number. So that means k into n1 or L into n2 is the period of this signal, right? So I hope you can find the I hope you understand how to find the period for these signals. So once you find the period, you can easily find the period of the individual. So using this equation, you can easily find the period of the resulting signal, which is x of n. So that's all about this part. So now let's start the basic signals we have put in the first slide, and we discuss them here. So the first signal we are going to discuss is the unit step signal or unit step function, which is defined as in continuous time case, which is denoted by u of t, and it is defined as it's equal to 1 for t is greater than 0, and it is equal to 0 for t is less than 0, right? At unit step is piecewise continuous, but it has a discontinuity at t equals to 0, right? So at t equals to 0, it is discontinuous. So here is how we the graph of the or the look like for the step function in continuous case. So you can see at 0 it has a value of 0, and again at z it has a value, at 0 it has value of 1. So that means it is discontinuous at this point, right? So uh, in case of discrete time step function, it is defined as u of n, and that's straightforward here because there's no discontinuity involved. So when its argument, which is n, is less than 0, that is for negative value of its argument, it is equal to 0, whereas if its argument is positive, positive means you understand that anything 0 or greater than 0 is considered to be positive. So in that case its argument, its output or its value is 1. So here is how it is plotted, right? So for 0 it has value 1, for 1 and up to infinity it has value of 1, right? So for less than um, uh, 0, right? So in case of discrete time signal, you understand less than 0 means -1, -2, -3, and so on, right? So for these values, the signal or the step function is basically 0. So step function is very useful to describe the signals in the compact form. We can write many other signals in terms of step function, right? So for example, we have a signal x of t equals to e power minus t. For this range, you understand this is the mathematical description for this signal, right? If I plot this signal, so first let me ask you, what do you think for this value, these values of t, right? For example, a is some, right? For example, a has some positive value. That means I can write a is greater than 0. So if a is greater than 0, what do you think? What is the, how this function is it uh, continuous value signal or discrete value signal, right? So when you look at the signal, you must think whether it's a continuous or discrete. So based on the independent variable, you can tell whether it's a continuous or discrete. And then again, the other important thing there, is it a periodic or aperiodic, right? So you have learned, I think you have done almost all the basic signals classification. So I think you should know by now you should know what type of signal is this one, right? So if a is positive, that means you have some negative here, right? So when t increases, that negative value increases, and when that negative value increases means this is basically exponentially decaying signal. So because we say the signal exists from 0 up to right, for t equal to or greater than 0, right? So that means we have the exponentially decaying signal, right? Something like this. Okay, so this is the t-axis, and this is the value of the signal x of t. So if you look at this one, the value of x of t is decreasing when t is increasing, right? So that's how the graph of this signal will look like. Now if we look at the description that we have to mention here, that this signal exists from this to this and 0 otherwise, right? But if we use the step function with it, so you see the two statements, you see how it simplifies the notation of the signal, right? So you see that's a very simple description. We say x of t equals to e power minus at u of t, and in case of here you understand you have to mention this thing, and this thing. So I hope the description of the signals using the step function is very compact. So I hope that clears you the idea, right? So similar is the case for the discrete time, right? So if you look at this one, again, what type of signal this will be? So just you look at the mathematical description, so you should just focus whether it's a periodic signal, continuous, or discrete, or periodic, aperiodic, exponential, and so on, because there are only two variable involved, right? You understand, because in this particular case we have only the independent variable, one independent variable, so that means we are going to discuss the one-dimensional signal. So in one-dimensional signal, right, in case of continuous time, we have t as independent variable, right? So t is variable, a is a constant, so a has depending on the value of a, right? So for example, let's talk again about this one. What will be the resulting waveform if a is positive here, negative, right? For example, a is less than 0, right? So in that case you must know that this signal will be exponentially, because at t equals to 0 it will be something like what will be the value at t equals to 0? So it will be equal to 1. So it will be exponentially growing, right? Because t is negative and we already have an a is negative and we already have a negative here. So depending upon the value of a, it can be exponentially growing or it can be exponentially decaying, right? So again we come here. So in case of discrete time signal, we have something like right? So because discrete time signal, so it will have the values at discrete intervals, right? So along this axis we have n, and along this axis we have the values of the signal, right? So because it says it's equal to n and n cannot be negative, so that means you have uh, for n equals to 0 it will have a value of 0, right? So this is value 0, n equals to 1, it has value 1, n equals to 2, value is 2, n equals to 3, right? So this is your growing signal. Is it exponentially growing or it's normally growing signal? Okay, so that I leave it to you. So you understand the description, right? Here we have defined or described the signal in terms of the mathematical notation. So this is the mathematical notation for this discrete time signal. So you understand we have to write about, look at the description, right? This one, and if you write the same signal in terms of the using the step function, right? So it simplifies the description of the signals. Okay. There's another important signal that is called the impulse, right? So in case of discrete time, we say discrete time unit impulse or unit sample or Kronecker delta function. That's very important signal, and we will discuss it in more detail in the second chapter when we'll talk about the linear LTI system. And okay, so the unit impulse function can be defined as, right, sigma n equals to 1 when n equals to 0, and sigma and this is equal to 0 when n is not equal to 0, right? So what does that mean? It means when its argument, right, the argument of the signal is n, right? So when the argument is 0, this signal is 1, and when argument is not equal to 0, this signal is 0. So this is how we represent it graphically. So you see the x of n, right, equals to impulse of n, and because impulse equals to 1 only when its argument is 0. In this case argument is n, so argument is 0 will be at this point. So at this point it is 1. For all other points, whether you go in the positive direction of the n or you go in the negative direction of n, we find that this signal is 0, right? So because we have discussed about the step function, continuous time, and discrete time, so let's see what is the relationship of the impulse function, discrete time impulse function with the discrete time step function, right? So it can be defined as the impulse function is basically the first difference of the step function, that is impulse of n equals to u of n minus u of n minus 1, right? So you understand by definition impulse of n should be 1 only when its argument is 0. So let's put something other than 1 here. So for example, impulse of 0 should be equal to what, right? So impulse of 0 by definition it is equal to 1. So if I put here, that means u of 0 minus u of because it's I'm replacing n with 0, so 0 minus 1 will be equal to, okay, minus 1. So what should be its value? Okay, so because u of 0, the step function, the definition of discrete time step function is it is equal to 1 when its argument is 0 or greater. So because its argument is 0, so that means its value will be 1. Again here u of minus 1, so definitely 0. Why? Because by the definition step function of the step function, it is equal to 1 only when its argument is positive. So you get 1 minus 0 equals to 1, and also by definition you know that impulse of this will be equal to 1 when n equals to 1. That means, right? So again, what will be the value of this when this is equal to 1? So impulse of 1 should be equal to what? Impulse of 1 should be equal to 0. Why? Because its value is 1 only when its argument is 0. In this case its argument is 1. When argument is 1, that means its value should be 0. So let's put here, that means I have replaced n with 1. So u of n means u of 1, right, minus u of, again n is 1, so 1 minus 1, 0, so it will be u of 0. So because what is the definition of step function? By the definition of step function equals to 1 when its argument is 0 or greater. Now in this case argument is 1, so its value will be 1, minus argument is 0, so again its value will be 1, so that will result into 0. So again by definition impulse of 1 should be 0, and that's exactly what we get. Okay, so so the second property is the sampling property. So based on this, we say x of n multiplied by impulse of n, it will be equal to x of 0 into impulse of 0, right? So you get the 0th sample for this, right? Now again, x of n into impulse of n minus n naught. So you understand this basically impulse of n minus n naught, right? Can you recall what is this? Right, so yes, so it's basically the shifted version of impulse of n. So if we shift the signal by amount of n naught, right? So in this case this signal, which is impulse of n minus n naught, this will only be equal to 1 when n equals to n naught, because when n equals to n naught this signal is 1, right? And else it will be 0. So we can write at this shift, for the shifted case, the sample value of x of n will be equal to x of n minus x of n naught times the impulse of n minus n naught. So the relationship between step and the impulse function. So step impulse function can be written as the first difference of the step function, that is already discussed in the previous slide. And this side we are going to discuss the step function in terms of the impulse function. So step function equals to summation of m running from minus infinity up to n impulse of m, right? What you understand by definition, you must keep the definition in your mind, then it's very straightforward. You understand step function has value of 1 when its argument is positive. That means when its argument is 0 or greater than 0, in that case its step function is 1, otherwise it will be 0, right? So by looking at this new notation, so if we look at the graph, right, so here in the top figure, right, you understand n is less than 0 because you see here 0 is here, then these are positive values and these are the negative values. So if I sum the impulse, that is from minus infinity up to n, in this case n is less than 0, so you understand it will result into 0. Also by definition of the step function, because n is less than 0, so it must be 0, right? The second case we take is this one as described here. What does that mean? It means if we sum the impulse from minus infinity up to n, and in this case you can see it's clear that the value of n is greater than 0. So in this case it will result into 1, and also by the definition of step function the value should be 1 because n is greater than or equal to 0, right? So so I hope you understand that this equation and these graphs show that the step function will be can also be expressed in terms of the impulse function, right? So let's go for the alternate derivation of the step function. So you know m running from minus infinity up to n, so let's change the variable of summation, right? So by changing the variable of summation, let me say k equals to, for example, k equals to n minus m, right? You understand m is the variable of summation here, so that means we can say that this implies that m equals to n minus k. So let's put the limit when m equals to so let's take the limits also when m equals to minus infinity. So k, because k equals to n minus, so m, that means the upper limit of the k will be infinity, right? Similarly, when m equals to n, right, that is the upper limit. Okay, the lower limit for m was minus infinity, so based on this value the limit for k will be plus infinity, and the upper limit for m is n, so based on this the value of k will be n minus n, so which is equal to 0, right? So that means we can say that step function u of n equals to summation k running from infinity up to 0, and it will be impulse of, right, when you say k equals to n minus m, that means m equals to n minus k, so we can replace m, right? Here m a, so m equals to n minus k. So that means, or because the norm is you put the lower limit first, so that means k running from 0 up to infinity, impulse of n minus k. So this is alternate expression and mostly used expression for the step function in terms of impulses, right? So that's the expression for. Okay, so based on this expression, uh, if we graphically uh, plot this one, so you see again the the limits for k are fixed, that is from 0 up to infinity, right? And this is the step function, so let's graphically represented the step function so that it's clear for you to understand how it looks like. Okay, now so we take here this the first case. Here if you see, this is the 0 point and n is somewhere here, right? So if I sum this from 0 up to infinity, right? If I sum from 0 up to infinity, this should result, this must result into 0. Why? Because from 0 up to infinity for all values, the impulse signal is 0. You understand? The impulse signal will only be 1 when its argument is 0. So because for these values of k, the argument cannot be 0, right? Because for example, n here is, maybe we say, okay, it's -5. So if I subtract from -5, 0 to infinity, so all these comes into some negative value, right? But right, and impulse will only be as shown here, 1. At this point it will be 1. Why it will be 1? Because at this point this has negative value, and k also has negative value, and there's negative here, so this negative plus the negative of the k becomes positive, and this positive and this positive will result into cancellation, which means here at this point the impulse will have 0 argument, so it will be 1. So because our interval of summation is here from 0 up to infinity, right, like k equals to 0 up to infinity, so it will result into 0, and it must result, because why? Because step function is only 1 when its argument is 0 or greater than 0, but here the argument is negative. If you look at this second figure, you see now this summation must result into one non-zero value. And why it should be non-zero? Because now n is greater than 0, right? So I hope this gives you some intuition and understanding the relationship between the step function and impulse function, right? So another the step, this was the about the step function in discrete time. Now we are going to discuss step function in the continuous time case. The relation, not the step function, the impulse function in continuous time case, and then the relationship between the continuous time impulse and continuous time step function, right? So if you look at this one, we define it that amplitude of impulse function equals to 0 when its argument is not equal to 0. It's exactly similar to what we had for the continuous discrete time case. And here we define the area. So area enclosed by the step function equals to 1. So how it is 1? For example, we take uh, you understand, area equals to width, which, okay, time the, so here we take width equal to, for example, we represent it by e, right? and the height equals to, for example, 1 by e. Okay, so here in this particular case, to derive the expression, we say the width of the pulse or impulse function is e and its height is 1 by e. So definitely its area will be equal to 1, because area equals to width time the height. So if width is e and height is 1 by e, in that case the area will be equal to 1, right? So if you look at this case here, the width is very big, right? So it has a big width, and the correspondingly the height of this is small, right? Now if I compress this, it will result into this another impulse which has smaller width but higher height, and maintaining the area same. If I further compress this one, it will result into a further reduction in the width and increase in height, right? So in the limiting case, when the width of the signal becomes 0, in that case we say its height will tend to infinity and the area enclosed will be 1, right? So that's the definition, that although it's practically not possible, but theoretically we say that its width should be around 0 or approximate to 0. So in case of discrete continuous time impulse, we say continuous time impulse is even function of the time, that is impulse of minus t equals to impulse of t, because you know that from this side all around up to infinity it is 0, and again this side all around up to infinity it is 0. So it is the even function. Around 0 it has 1, so that means it is even function of the time. Again, the property we discussed for the discrete time case was the sampling property. So any signal multiplied by impulse equals to, so that means impulse of t, this will result into phi of 0 times the impulse of t, because at the argument of the impulse at here is t. So that means at t equals to 0, it will be non-zero. So in that case we get the value of the phi of t at 0. So in generalized form we can write that phi of t times impulse of t minus t naught. So I hope you get the idea that t minus t naught is basically the shifted impulse, right? So you understand if you can recall the operations on the independent variables. So we had 3 operations: scaling, shifting, and reflection. So this equation shows the shift operation. So if we have a shifted impulse, you understand the shifted impulse will have a non-zero value at when its argument is 0, right? So in this case that means the impulse will have value of 1 at t equals to t naught, right? So at t equals t naught, this signal will the impulse will have non-zero value. So that means if you multiply these two, you understand in multiplication, if one quantity is 0, the product of the two will result into 0. Now because this signal is 0 for all values except when its argument is 0, so that means when its argument is 0, what is the point where its argument will be 0? The point will be when t equals to t naught. So when t and t naught they have same value, so subtracting them will result into 0, and when this result into 0, the impulse will have non-zero value. So that means this impulse will have non-zero value at t equals to t naught. So if I multiply these two signal, because this signal has value, for example, we assume that this signal exists from minus infinity up to infinity, but because this signal which is multiplied with this one has non-zero value only at t equals to t naught. So that means from minus infinity up to infinity, all the values of this will be 0. So multiplying the two will result into 0, except the point where t equals to t naught. At that point, this will be non-zero. So we can say that the product will be equal to phi of t naught impulse of t minus t naught, similar to what we had for the continuous time case. Right, so the relationship between the step function and the continuous time step function and continuous time impulse function. Right, so again, from the previous discussion, we have this expression. So integration of this from minus infinity up to infinity will result into this and this, and because by definition from minus infinity to infinity, integration of the step function will result into 1. So that means multiplication of 1 equals to this, or in short, the shifting property can be stated as the integration of minus infinity this into impulse of t minus t naught will, I think we will discuss it in more detail in subsequent topics. So this is the shifting property. So similar to the relationship we had for the discrete time case, in continuous time case, because you understand in discrete time case the relationship between the impulse function and step function was that we said impulse function equals to the first difference of the step function. Okay, so here, because this is continuous, so in continuous we have instead of difference we have the derivative. So we say, okay, impulse function equals to derivative of the step function. Similarly, we defined the unit step function in terms of the impulse function as the summation, right? So if you recall, we said u of n equals to summation, right, k running from 0 up to infinity impulse of n minus k, right? So in case of continuous time, we again have the similar relation. So in continuous time case, instead of summation we have the integration. So it is expressed as summation, right? So u of t equals to impulse of tau d tau, and its integration over integration from minus infinity up to t. So this is an example, and you must go through it and simplify the expression, right? So answer is also given, so I hope you can go through it. The next function we are going to discuss here is the rectangular pulse function. Rectangular pulse function in continuous time case is represented by rect with the argument t by tau, right? And tau represents its width. So this is equal to 1 when absolute of t is less than or greater than tau by 2. So for example, this is tau by 2. So if t is greater than tau by 2, or t is less than or minus t is less than, right? So minus tau by 2. So in that case it will be 0. whereas for the case when absolute value of the t is less than or equal to tau by 2, it will be 1. So this is the case, right? Or in case of discrete time signal, so it's represented, I think it's quite straightforward, so you can go. Okay, so another question or another thing is a pulse signal can be extra in terms of the step functions, right? So in terms of step function, we say, for example, we have step function which is uh, uh, not step pulse not step function, pulse function, right? So we have, for example, a pulse function which is value of 1 from 2 up to 4 and 0 beyond this and before this. Okay, so to represent this in terms of step function, that's quite straightforward. If you because it's 1 from 2 onwards, so step function, you understand, step function equals to 1 when its argument, in continuous case when its t is greater than 0. So the because in this case it should be 1 from 2 onwards, so that means we can use the shifted step function. So the shifted step function will have value of 1 when its argument is equal to or greater than 2, right? So that's the one. Okay, now because I want it to stay 2 from 2 up to stay 1 from 2 up to 4, so that means I need another step function. How many units shifted? 4 units shifted with negative amplitude, right? So I get this one, minus t ut of 4. So what does that mean? That means this is basically u of t minus 4. So u of t minus 4 would be something like this. This is right. So this is 4 means it is 4 units shifted. If you recall that we had a generalized expression for the shift was x of t minus so x of t minus t naught. So this is expression for the shift, right? So if t naught is positive, then it will be shifted right, you know, and if t naught is negative, in that case it will be shifted left. So in this case, like 2, so if you compare with standard equation, 2 means t naught equals to plus 2, right? So if it's plus 2, that means it will be shifted right 2 units. So originally step function starts from here, right? You understand, from 0. Okay, you understand, at 0 it is discontinuous. Why it is discontinuous? Because at 0 it has value of 0 and also its value is 1. Okay, so originally if not shifted, then step function equals to this, right? Step function equals to this. But for the shifted case, we have step function, for example, 2 unit shifted. So this is the 2 unit shifted case of the step function. Again, this is 4 unit. Why we want 2 unit and 4 unit? Because we want to have value of 1 at 2. So that means if I use step function and shift it by 2 units, I will get one value, right? I will get value equal to 1 from 2 up to infinity. But I don't want from 2 up to infinity. I only want 2 up to 4. So that means I need another step function which is how many units shifted? 4 units shifted with, right? So if I take negative of this one, right, this, you understand, this is the negative, means this point is basically indicating the scaling of the dependent variable. You understand, in case of signals we have only two variable. One is independent variable, that's why we call it one-dimensional signal, and the other is dependent variable. So x of t is basically dependent variable and t is independent variable, right? So if I multiply anything here, that means I am scaling the signal, right? So for example, minus 1 means I have scaled the signal by a factor of 1, but minus means it will be inverted. So already if it is positive, it will become negative. If already it is negative, then it will become positive, because you know step function is positive. So already it was positive, now it will become negative. So you get this signal. Now if I add the two, so you know from this point, right, from 2 up to minus infinity and from 2 up to minus infinity, both the signal has value of 0, so 0 plus 0 will result into 0, right? So this will result into 0. Now from 2 up to 4, right? From 2 up to 4, from 2 up to 4, this signal is 1 and this signal is 0, so 1 plus 0, it will result into 1. So you get this signal. Okay, again from 4 and beyond, this signal is minus 1 and this signal is plus 1, so plus 1 plus minus 1, it will result into 0. So that means from 4 up to infinity, this will result into 0. So that means this signal, which is a pulse signal, can be expressed in terms of the step function like this. So it will be u of t minus 2 minus u of t minus 4. So I think that's all for today, and try to go through the slides and the video lecture and think over each and everything over and over again. These are the basics. So if you are good in signals, the following topic will be the systems, and if you are very good in signals and system, then I think it will be easy for you to understand the subsequent topics, which are convolution and the Fourier series transform and so on. So I hope that will be, for sure, that will be very easy for you if you understand these. But if you don't understand these, then it will be not only difficult this part for you, but also the subsequent part, right? So try to clear your concepts and think over each and every equation, waveform, description, and so on. So you will realize that it's quite straightforward and very easy subject. But if you don't understand, then it's very difficult. You cannot memorize, and it will be very hard for you. So okay, see you. Allah Hafiz.